x86 versus ARM. Two instruction sets, born 7 years apart, that split computing in two. Today we take both of them apart, down to the bytes, and find out what actually separates them, and what never did. Here is the puzzle. Two machines render the same scene. The desktop draws 125 watts. The tablet draws less than 6. Same job, roughly the same time, 21 times the energy. For decades, the popular explanation was the instruction set. x86 is power-hungry, ARM is efficient. That explanation is mostly wrong, and the ways in which it is slightly right are far more interesting. To see them, we have to start at the contract. An instruction set architecture is a contract. Above-the-line software, compilers emit patterns of bits. Below-the-line silicon, the vendor promises that each pattern triggers exactly the behavior the manual specifies. Here is the 64-bit ARM encoding of an add, 32 bits, with fields for the operation, the two source registers, and the destination. The hardware decodes those fields, fires the arithmetic unit, and writes the result back. Notice what the contract does not say. It says nothing about how the silicon does any of this. That freedom is why this whole war is subtler than it looks. The two contracts were written in different worlds. x86 ships in 1978, when memory is the most expensive part of the machine. So instructions are dense, anywhere from 1 to 15 bytes, and a single instruction can read memory, do arithmetic, and write the result back to memory. Today the family carries roughly 3,500 instructions. ARM arrives in 1985 at Acorn from a tiny team that could not afford complexity. Every instruction is exactly 4 bytes. Only loads and stores touch memory. The first ARM ran on about 25,000 transistors. Density versus regularity, that one trade is the root of everything downstream. And here is where it bites. A modern core wants to decode many instructions every clock cycle. On ARM, boundaries are free. Every 4th byte starts a new instruction, so you can put 8 or 10 decoders on the stream in parallel, instantly. On x86, the length of an instruction is only known after you have passed it. The opcode, the prefixes, the addressing byte. Finding where instruction 5 starts means chewing through instructions 1 to 4 first. The work is inherently serial. Real x86 decoders attack this with brute force, speculatively decoding at many offsets at once, and brute force costs transistors and watts. x86 found an elegant escape in the 1990s. Stop executing x86 directly. The decoder translates each architectural instruction into one or more microops, small fixed format, load store operations. A read, modify, write, add becomes a load, an add, and a store. Past the decoder, every x86 core has been a RISC machine since the Pentium Pro. Then add a microop cache. Once a hot loop has been decoded, the translations replay from the cache, and the legacy decoder sits dark. The tax is real, but you mostly pay it once. So what difference is left? Because ARM decode is cheap, designers pushed it hard. Apple's Firestorm core went 8 wide in 2020, when flagship x86 cores were 4 or 6. Apple's M4 decodes 10 instructions per cycle and keeps around 650 instructions in flight. And width buys efficiency. At a fixed level of performance, a wider core can run at a lower clock, and power scales roughly with the cube of frequency once you count the voltage that comes with it. Wide and slow beats, narrow and hot. x86 is catching up, but it had to fight its own decoder to get there. There is a second, quieter difference. What stores promise? x86 guarantees store order. Every core sees one core's writes in the order the program issued them, and the hardware must maintain that illusion, draining store buffers in order. ARM is weakly ordered. The core may let stores and loads pass each other whenever that helps, and when your algorithm cares, you say so explicitly. With a barrier instruction like DMB, watch the ARM side. I arrives before X, so the observer briefly sees a state that never existed in program order. That is legal. Weak ordering gives hardware room to optimize, but it moves the burden onto software, and porting lock-free x86 code to ARM is where careers go to be humbled. Now the myth itself. Measure where a modern core actually spends its power. Clock distribution, the out-of-order machinery, caches and translation buffers, the execution units. Decode, the famous x86 tax, is a sliver, a few percent on a big core. A 2013 study at Wisconsin compared ARM and x86 chips head-to-head and found the instruction set largely disappears into the microarchitecture. Phones sip power because they were designed to, built for a 5-watt budget, integrated as a single system on chip and racing to sleep, finishing each burst of work and collapsing into a near-zero idle state. The instruction set is not destiny. It is a thumb on the scale. But thumbs matter at scale. Plot performance against power, and the modern ARM cores sit far up and to the left. In these representative curves, the same benchmark score at roughly a third of the watts. Apple proved it in laptops, with M-series chips matching desktop parts at a fraction of the power. Amazon proved it in the data center, where Graviton now underpins a huge share of new capacity, because performance per dollar follows performance per watt. Qualcomm is pushing the same bet into Windows machines. None of this is magic instruction set physics. It is what cheap, wide decode lets a motivated design team build. So why does x86 still own the desktop and most of the server market? Because the contract is also a moat. 45 years of compiled binaries, games, drivers, enterprise software that nobody can rebuild. That inertia is worth more than watts, but the moat is draining. Rosetta 2 and Microsoft's Prism translate x86 binaries to ARM on the fly, at 80 to 90% of native speed, and they catch the result, so the tax fades after the first run. What resists is the residue, kernel drivers, hand-tuned vector code, anything that talks to hardware directly. Inside the chip, the war is over. Both camps build the same animal, a wide, speculative, out-of-order machine, with a different decoder bolted on the front. What the instruction set still decides is who is allowed to build that machine, and on what license. And that, not the bytes, is the war that remains. Thanks for watching.